Hello everybody, welcome back to another episode of the problem solving series. As promised in the torque video, today we are going to be covering static equilibrium. So static equilibrium is going to hit on three concepts. So we're going to be looking at the sum of the forces in x and y, so both of our linear Newton's laws as well as the sum of the torques. So our two linear and our one rotational Newton's laws that we have, and all three of those are going to be equal to 0. And I cannot stress this enough, this is the most important thing I would probably say about static equilibrium, is that it can be about any point on the lever arm. So it doesn't have to just be the axis of rotation. Any single point anywhere along the lever arm, if you pick that point to be your axis of rotation and you add the forces in x and y and the torques, all three of them should sum to 0. So this is really helpful when solving some problems, because if there are some forces or distances or things that are unknown, it might be really convenient to pick that point at the location of the unknown forces to go ahead and pick that as your rotation point. Then your distances, when you look at your torques, would be 0, because technically that would be our origin, and then all of a sudden those forces disappear. So, yeah, that's pretty much it. There's not really any new physics involved, so the torques are still just the perpendicular force component times the distance from whatever point we're picking to be our axis of rotation. Our forces are MA. And yeah, so let's just jump into some examples.
Two people who each weigh 55 kilograms are sitting on a bench, drawn below. If the person on the left side stands up, will the bench flip over? Okay, one thing I forgot to put on here that I just realized is the mass of the bench is going to be 5 kilograms. So let's do mass bench. Just write that on here. While I'm writing givens, I'll go ahead and write the mass of the person is the 55 kilograms. And I'm not going to include the length. I'm trying to show that we don't need it to solve some of these problems. If we can write all the lengths of where the forces are being applied in terms of the overall length, then we'll get stuff canceling. So I'm just going to leave that written as is. So we have our picture drawn. The first thing I like to do with static equilibrium is draw an even more simplified picture. So just kind of showing the lever arm, or the object that's going to be the one that's rotating, with just the forces drawn on them. I won't end the axis of rotation if I know it at the time. So I'm going to draw this, but without one of the people on the left. So I'll draw an X through him, just so we know we're not including him. Okay, so we're going to have just a straight line. We're still labeling this end as 0. We'll have a normal force from the one leg that I'll call Fn1, located at L/3. We'll have the force of gravity from the center of mass, Fg center of mass, at L/2. We'll have the normal force from the second leg, Fn2, at 2L/3. And then lastly, we're going to have mg from our person at 5L/6 away. So if we're interested in seeing when something's going to be tipping, we want to draw our axis of rotation at the last point of contact, or the edge that it would be rotating around. So if the weight of this person on the right is going to be causing this thing to tip, then that means that the table would be rotating about the leg with normal force too. So I'm just going to draw that with an arrow or with an X right there, then we can go ahead and look at, mainly I'm just going to look at the sum of the torques. Since we don't know the normal force from either of the legs, putting the axis of rotation at the one where it's going to be flipping eliminates needing to know that force when looking at torques, and we'll calculate and just check if what does the normal force one need to be in order for these torques to add to 0. So yeah, I guess I'll write that too. So thinking about what does Fn1 and Fn2, actually we would be checking both of them. Need to be to keep sum of the torques equal to 0. So that's where we'll start. So our sum of our torques equals 0. Let me go ahead and draw a counterclockwise positive, clockwise negative. Then we'll look at each of our forces. So our Fn1 is going to give us a negative torque since it is going to be trying to push this clockwise. So we'll have a negative torque from normal 1. We'll have a positive torque from FG center of mass. That's going to be trying to push us counterclockwise, so plus torque center of mass. And then Fn2 is at the pivot point, so that won't give us a torque, like I already said. And then the FG person is going to be trying to rotate this clockwise, so that will also be a negative torque provided by the person's weight equals 0. So okay, let's sub in our force times distance for each of these. So I'll have negative Fn1 L over 3 plus Fg center of mass L over 2 minus Fg person 5L over 6. Oh, actually, something I just realized. So these distances that I put in here are the distances measured from the 0 end, not the distances measured from the pivot point. So I'm actually, okay, let me rewrite each of those. So for Fn1, negative Fn1, and then to calculate the distance here, we're going to take the x value from at the pivot point, so 2L over 3, and subtract the where the normal force is that we're calculating the torque for, which would be the L over 3. For the plus, I'm just going to substitute in mg now. Center of mass, g, that would be 2L over 3 minus L over 2. So again, just taking the pivot point position, subtracting the center of mass position, and that'll give us the new coordinates with respect to the 2L over 3. And then we will have negative m person, g, and this one will be 5L over 6 minus 2L over 3. So I will say, also note that you want to always take the larger position minus the smaller position. We already take the sign into account when writing the torques themselves. So we want to take the absolute value of the distances and the absolute value of the forces, since we are already writing whether the torque is going to be positive or negative before we substitute in our force or our distance. But okay, that being said, so we'll simplify. We can still cancel out an L from each of these terms. And in the next step, I will just simplify all those fractions. Okay, so when I do that, I'm going to go ahead and add our Fn1 or 1/3 Fn1 to both sides. Should give us m center of mass g over 6 minus m person g over 6 equals Fn1 over 3. We can cancel out a 1/3 from all sides, so that will go away. That 6 will become a 2, and that 6 will become a 2. And then we can go ahead and plug in from here and see what our normal force would be. So we're going to have 5, 9.8 over 2 minus 55, 9.8 over 2. And that gives me negative 245 newtons. Okay, so conceptual check. We can't have a negative normal force from a leg of a bench that's sitting underneath the table. So this would not be a possible force for us to have with the setup that we have, which tells us that this bench would indeed flip. So give people some warning when you're standing up from a bench because you might tip somebody over. A ladder is leaning against a frictionless wall in the figure below. If the ladder is 10 kilograms and 6 meters long, what are the normal forces acting on the ladder? And what is the coefficient of static friction needed to keep the ladder stationary? This is going to be, so the wall is frictionless, but the floor is not. Okay, so static equilibrium problem. We already kind of have our sketch in pretty bare bones. We wouldn't need to simplify it anymore, but we are going to want to go ahead and draw all of our forces on here. So we have, first we'll have the center of mass of the ladder itself, so Fg center of mass. We'll have a normal force from the wall, so Fnw. We'll have a normal force from the floor, Fnf, and then we will also have static friction pointing to the right, little fs, from the floor. All right, and we're going to set up. So we need to know Fnw, we need to know Fnf, and we need to know mu s. We know that our mass is 10 kilograms and our length is 6 meters. Alrighty, so let's set up some of our forces first, and then once those are set up, we can see maybe where the best place would be to put our pivot point to calculate the torques. I will say right off the bat, it's going to be easiest for us to put that pivot point at either the wall or where the ladder is touching the floor, because that'll either way to eliminate one of the forces that we don't know. Probably going to end up putting it at the floor since there's also an unknown in the friction there, and if we put the pivot point at the bottom, then the torque from both of those forces will be 0. So yeah, let's do sum of forces in the x equals 0, which will be our force of static friction minus our force normal from the wall equals 0. We can substitute in that the force of static friction is going to be the coefficient of static friction times the normal force of the floor. So I also will note here, just because you can sometimes have problems that are similar to this, but the wall does have friction and the floor has friction. Just remember that the frictional forces for each surface are going to be equal to the coefficient of friction for that surface times the normal force being exerted by that surface. So I know it might get a little confusing if you have multiple normal forces, but just keep in mind that you want to keep track of that stuff. All right, so then from here, all I'm going to do is just add the normal force of the wall over to the other side. That's really as far as we can take this equation. So we'll have mu s normal force floor equals normal force wall. We'll do sum of the forces in the y equals 0, where that'll just be normal force the floor minus mg equals 0. Again, I'm just going to add the mg over to kind of take that as far as we can. And when we do, we see that this equation on its own is going to give us the normal force from the floor. So I will go ahead and just plug those values in for m and g. So the normal force for the floor be 10 times 9.8, so it'll be 98 newtons. So yeah, I am going to stick with what I said at the beginning. I'm going to say that the sum, well, I guess I'll do this underneath the y's since we still have some ways to go with the x's. So the sum of the torques equals 0. I'll throw the counterclockwise positive, clockwise negative symbol up there. And in light blue, I'm just going to throw an axis of rotation symbol. Oh, and then what we're going to need to do from the geometry is get the angle between the lever arm and the forces. So I'm going to, just with the dashed line, extend the force gravity vector down from the rule for right triangles, or for any triangles. The angles have to add to 180. So if that vertical FG center of mass extension is going to make a right angle with the horizontal from the floor, since that bottom left angle is 50, then that tells us that the angle between FG and the ladder is going to be 40 degrees. And then for the normal force from the wall from alternate interior angles, that angle is going to be 50 degrees. So when we take our torques, our FG center of mass is going to be negative. So we'll have a negative torque from the center of mass, and the normal force from the wall is going to give us a positive torque. The torque center of mass is going to be our mg times the distance from the pivot, which is going to be L over 2, and then times the sine of 40. Our tau from the wall will be the normal force from the wall times L times sine 50, and that is all equal to 0. So we can cancel out an M, or nope, we can cancel out an L. And then I'm going to add the whole mg sine 40 over 2 to the other side to simplify. So I'll have F normal wall sine 50 equals mg sine 40 over 2. We could divide both sides by sine 50. And then we have an expression for the normal force from the wall. So sine 40 to sine 50. And then we could go ahead and plug in our mass and G. So 10, 9.8. And this gives me that the normal force from the wall is going to be 41.1 newtons. And last but not least, we can go ahead and plug in the normal force of the wall and the normal force of the floor into that sum of the x expression that we came to and solve for mu s. So mu s is just going to be equal to the normal force from the wall divided by the normal force from the floor, which will be 41.1 divided by 98, and that gives me 0.42.
And there you have it. So that is static equilibrium in a nutshell. I do like these problems, especially for those kind of more exercise science geared individuals, because it's one of the places that we can really show examples and do problems that correspond to ligaments and muscles and things in the human body, and see kind of how the location of inserts, of where your ligaments or muscles insert can affect your baseline strength, I guess. As a weightlifter, I always find that really interesting, and I think about it as I'm lifting or doing any type of exercise. So yeah, that's all I have for this video, and until next time, happy physicsing. Are you supposed to be chewing on this? Hey. Hey. Don't you do it. Don't. I'm gonna say bye to the kiddos. We're gonna go for a walk. No.